Hey people, hi. Hopefully you have this paper in front of you and you can hear me, and we're going to go through the notes on the first paper, and then the homework will be the second paper due Monday. All right, so here we go. Are you ready? If you get confused or have a question, please have the sub stop this at any point and you guys can talk it over and figure it out. All right, so here's the deal. Continuity, layman's terms, is the ability to draw a graph without lifting your pencil and having all points in between defined. It's a little beefier or more picky than limits existing, so you'll see they relate, but their continuity is a little more. All right, so check this out. There are three conditions that need to be met in order for continuity to happen. First of all, f at c must be defined. It can't be the case that when x equals c, you don't know what to do. So it can't be the case that the graph looks like this and there is nothing at c. It can't be the case that a piecewise function never tells you what to do at c. It doesn't say, hey, when x is c, do this. This is strictly what to do unless greater, but not at. So if that's the case, then you already can't be continuous there because the point doesn't even exist. The second thing for continuity is that the left hand and the right hand have to agree so that there's no jump. It has to be the case that the one-sided limits are both equal, so you'll have to prove the one-sided limits are equal in step 2. And in part 3 or condition 3, you'll have to prove that the point and the limits are the same. It's not the case that the point exists, but it's somewhere else besides the limit. So you'll have to prove that they're the same, all right? So that's the case, and now let's get into what some problems look like. First, reinforcing the concept. If I were to talk about this problem and say, why is f continuous at x equal 2, I could meet all the conditions. F at 2 is defined. It tells you there is a point at 2. It's also the case that the limit as x goes to 2 exists, and that's because the left hand and the right hand agree. Remember, the two-sided limit only exists if the left and right hand limits are equal, and I can see they are. And last but not least, I think you'll agree that the limit and the point are all one and the same, so because f of 2 equals what x is approaching, f is approaching as x goes to 2, it must be the case that f is continuous at 2. I could draw that curve without lifting my pencil. What about the second box here? Why is this not continuous? Which of the three conditions are not met in box 2? Okay, hopefully you said the first condition. F at 4 is not defined. They never told you, hey, at 4 you get this point. There's a hole there, all right? So condition 1 is violated. In the second one, is there a point at f at 4? Well, yeah, f at 4 is defined. And does the limit exist? Yeah, the left-hand, right-hand limits are the same, so condition 2 is met. But the third condition is the limit, or what it approaches, and what it is at 4 the same, and that is not true. So you would say f at 4 doesn't equal the limit as x approaches 4, and so condition 3 is violated. That's why it's not continuous at 4. All right? Hopefully that's going on. Now, let's talk about another type of problem. Right below it, determine if f is continuous at x equal -1 and x equal 3. So, check this out. Let's start with at x equal -1 over here. At x equal -1, let's meet the first condition. Do they tell you what to do when x is -1? Now, here not so much, but here yes. When x is -1, use this function, so it is defined. Condition 1 is met. What about the limit? Well, you have to do the one-sided limit. So this is actually two things you're going to need to do. -1 from the left. And -1 from the left, or less than, means use this branch. So I'm going to take the limit as x goes to -1 on 2x cubed minus 7x first. And that would approach something like 2 times -1 cubed minus 7 times -1. That's -2 plus 7, or 5. From the left, the y values are getting closer and closer to 5. From the right, the limit as x approaches -1 from the right. Well, that's above -1, so it uses this branch, 4 minus x. That's 4 minus -1, that's 5. And so the limit the two-sided limit, I'm just going to call this f of x because it's both branches, exists because the two one-sided limits are the same. All right, and last but not least, does the point equal the limits? And I think you'll agree that at -1, it's the same as the right-hand limit, and so it is the case that f at -1 is the same as the limit as x goes to -1, which is all 5. And so we can conclude, it's pretty typical when you write a proof that you do this little three-corner triangle dot to say, therefore, f is continuous at x equal -1, because the conditions for the definition of continuity have been met. All right, let's try at x equal 3. Do they tell you what to do when x equals 3? And this is equal to, so it is defined, f at 3 exists, or is defined. I guess you could say exists, but it's more common to say is defined. The limit as x goes to 3 from the left uses this branch, and that's 4 minus 3, so the left-hand limit is 1. The limit as x goes to 3 from the right uses this branch, that's x squared minus 10, which at 3 is 9 minus 10, that's -1. Well, that's bad. From the right it's 1, from the left it's -1. It cannot be continuous, so I can stop. At that point I can make my conclusion. F is not continuous at x equal 3. And if you wanted to justify it, you would say because the limit as x goes to 3 does not exist. Okay? Or you could say because the one-sided limits aren't the same. Okay, hopefully that's going well. Now you try. I guess depending on substitute, will you please pause this and let the students work on this, and we'll see how it goes. Tell the sub when she is ready to start it again. Okay, so here we go. Hopefully this went well. Let's see, at -2, hopefully you were starting with saying the first condition. Is f at -2 defined? It does tell you what to do at -2. F at -2 is defined. First condition met. The limit as x goes to -2 from the left uses sine of pi x, which is sine of -2 pi. That is 0. The limit as x goes to -2 from the right uses this branch, log of 3 plus x. As x goes to -2 by direct substitution, that's log of 3 minus 2, or log of 1. That means e to what power is 1, and that's the 0th power. Therefore, the limit as x goes to -2 exists, because the left and right hand limit are the same. And I think you'll agree that in terms of is the point equal to curve, well, the point is actually on the same function as the log curve, and so it is definitely the case that the point and the approach are the same. The limit and f at -2 both equal 0, and so we can conclude that f is continuous at x equal -2. Hopefully you got that right. Yes? It helps if you do bullets so I can tell where the conditions are met. All right, x equal 1. X equal 1. First of all, at x equal 1, when you put in 1, does it tell you what to do? Well, this is strictly greater than, this is strictly less than. It never tells you what to do when f is 1. F at 1 is not defined. And therefore, you can stop. F is not continuous at x equal. That was easy. Hey, that's good. Okay, so hopefully that went well. You'll practice that on tonight's homework. Let's go to the next idea. This is a pretty common problem also. It is a make it continuous problem. Imagine if you had a line and a parabola. Now you would, in order to get continuity, you would have to have those have good solid conditions to make them meet. So the problem is really, how do you make them meet at the point in between? So the idea is you meet the definition of continuity. Sorry. Hi, Rod. I'm recording my lesson.
You talked about continuity.
Okay, cool. All right. So here we go. The conditions need to be met. Now, actually, you don't even need to meet the conditions. As long as f at 4 is met, then you don't need to show the conditions are met. You're not proving continuity so much as solving a problem. Your end goal is not to make a proof, but to get what is A to make this continuous, right? So you don't need to meet all the bullet points. Instead, let's just go straight to meeting the limits. For the second condition, it must be the case that the limit as x goes to 4 from the left, which uses this function, ax plus 5, needs to equal the limit as x goes to 4 from the right, which would use this function, x squared minus x. Those have to be equal. Now, if you do that limit, surely it has to be the case that when x goes to 4, this becomes 4a plus 5. That's the limit you get out of that, depending on what a is. That needs to be the same as what this comes out to be, 4 squared minus 4. Well, I have to have the one-sided limits the same. For the one-sided limits to be the same, 4a plus 5 needs to equal 12, which means a needs to equal 7/4. Only by sloping that way would the two lines meet, right? That's the idea. Now try the second one on your own. Now you're going to have a little more work to do because you have two unknowns. So expect to do two different calculations of one-sided limits, one at -2 to get an AB equation, and one at 1 to get an AB equation. Then hopefully you'll have enough to find A and B. Try it on your own and work together if you like. Pause now. Okay, let's see how you did. First of all, we have to have continuity at -2. And for -2 to work, it has to be defined, which it is, but the one-sided limits have to be the same. So the limit as x goes to -2 from the left, which would use 2x plus 1, needs to equal the limit as x goes to -2 from the right, which would use ax squared plus b, because above 2, -2 would be right there, yeah? Now if you evaluate this limit, at -2, that would be -4 plus 1. And at -2, this would be 4a plus b. So you get something like -3 equals 4a plus b. Are you with me? Now that's great, but that's an equation I cannot solve because it's two unknowns and only one equation. So that's not going to go anywhere. I need to do more. So what about at 1? At x equal 1, it's also defined at 1, so we're cool, but we need one-sided limits to be the same at 1. So the limit as x goes to 1 from the left, which a little less than 1 would be this guy, ax squared plus b, needs to equal the limit as x goes to 1 from the right, which is a little above 1, so we use natural log of x. At 1, this guy would have an x value of 1. That's an x goes to 1. So that's a plus b equals log of 1. Log of 1 is 0. That's nice. Now between these two equations, we can solve. Probably by substitution would be easiest. Wouldn't you agree that a needs to equal the opposite of whatever b is? If I throw that in, then I get -3 equals -4b plus b, or -3 equals -3b, so b must be 1, which implies a must be the opposite, -1. How did you do? Did you win? I hope so. Those are hard. They take practice. The first one I did as an example was easier because there was only one unknown. You'll do a little bit of both. It's possible even you have 3 unknowns later on. We'll get there. All right. A little bit of vocabulary now. Here we go. You need to be able to identify there are 3 types of discontinuity and know the names for them. At x equal -8, yes, it's a whole, but it's more commonly called on an AP test or in a textbook called the removable discontinuity. Now they call it a removable discontinuity because I could remove the problem by redefining the point. If I put that point somewhere else, I could fill the hole. So that's a removable discontinuity. The problem is that usually at a removable discontinuity, the limit is not equal to the point at A or C or whatever you want, okay? At x equal -2, now this doesn't show well, but on the right-hand side, it's approaching asymptote behavior, so since it's a function, it shouldn't curve back. So this is called an infinite discontinuity. Technically, the limit doesn't even exist at infinity, and so if the limit doesn't exist, you can't have continuity there. All right, and last but not least, at x equals 6. That's a case where the left hand and the right hand, it jumps right up to a totally different point. That's called a jump discontinuity. And the case there is the limit as x approaches the number from the left is not equal to the limit as x approaches the number from the right. That's different. All right, so we have three types of discontinuity: removable, which is whole; infinite, which is an asymptote or jump. Okay, so looking at, I want to make sure I didn't have a problem underneath that. No. Okay, so looking at this problem here, we're trying to figure out where this has an infinite and a removable discontinuity. Now, an infinite discontinuity is when you get an asymptote, and that happens because you have 0 in the denominator, but not the numerator. It's undefined. Removable discontinuity is where you have 0 over 0. Well, it's hard to tell right now. I guess we could use quadratic formula, but it would be easier just to factor. Now, the top, some people shy away from trying to factor that, and that's a pity. They would rather do quadratic formula. I would prefer you just get better at factoring, so I'm going to do it that way. The denominator, let's warm up there. Do you agree the factors of x squared go in the first, and the factors of 20 go in the second spot? You want the factors of 20, -20, that can combine to -1. The factors of -20 that add to -1 are -5 and +4. All right? The numerator, the factors of 2x squared are 2x and x. Factors of 15, you could go 1 and 15 or 5 and 3. You could do the AC method. You could use quadratic formula. I'm more about a little bit of trial and error here. So I'm thinking 3 and 5, and I'm going to go with a 5 here and a 3 there because that would be 10x and 3x, and that could be a 7 if the 10 was negative and the 3 was positive. I feel like that works. Check me if you disagree. But I feel like that's right. So, A, the answer is an infinite discontinuity. Where is there non-zero over 0? Now, I think you'll agree these are the same, so that's removable. That's the 0 over 0 problem. That means we have a non-zero over 0 at -4. So we have a infinite discontinuity at x equal -4. We have a removable discontinuity at x equal 5. That's the idea. Factor, compare where there's zeros, and if it's 0 over 0, it's removable. If it's 0 in the denominator, it's infinite. All right? Let's try. I want to make sure I didn't skip any. Okay. I just added a page. Okay, sorry. So let's try this one. Determine the values of the asymptotes. Okay, now this means vertical, which we're going to use that skill we just did, and horizontal. Horizontal, you're going to need to go back to yesterday, and that's end behavior. You get a horizontal asymptote if the limit as x approaches infinity of a function is a constant. Then that means y starts to approach just one number. That's horizontal asymptote. So you're actually going to have two totally different types of problems here. One is factored and look for zeros, and the second is do an infinite limit and end behavior to make this call. So let's start with vertical. If I factor this, the top factors into something like, well, 2x and x, and 5 only factors either 1 and 5 or 5 and 1. Which one works? Well, 1 and 5 would be 10x and 1x. That feels like it would work if the 10x is positive and the 1x is negative. So I feel like that's right. The bottom, 3x squared is 3x and x. 5 is only, the factors of 5 go in the last spot, so it's 1 and 5 or 5 and 1. And let's go with 1 and 5 because that would be 15x and 1x. That works if they're both positive. All right. So there's my factorization. X equals -5, that is a whole. And in this case, that doesn't even help me because they don't ask about where is any removable discontinuity, so I guess I can blow that off. But this is not a common factor, and therefore there's a vertical asymptote at x equal -1/3. You have a vertical asymptote. All right, so that's part one. The vertical asymptote answer is done. Now, what about the horizontal asymptote? Does x start to, or does y start to approach a constant as we get further and further out? So the limit as x approaches infinity of this function, go back to the unfactored one. I think the original problem is easier if it's all multiplied out. Remember yesterday when we talked about end behavior? You look at the dominant term in the top and the bottom and compare. And what happens if the dominant terms are equal in power? The limit approaches the coefficient ratio. So the limit is 2/3. Now that's great, but we need to go a little bit more because that's the limit, not the equation of the asymptote. This means, remember when you do a limit, you're saying as x does its thing, what does y approach? If we just said y approaches 2/3, that's the horizontal asymptote then. If y approaches a constant, there is a horizontal asymptote at y equal 2/3 for this crazy graph. The limit isn't just useless, the limit actually tells us how the graph behaves on the outside. Okay? Now if I were to do this at -infinity, it would actually be the same because it's squared and squared. So there isn't a second different vertical or horizontal asymptote on the left side. It's the same. But I did look. It's important to look at both places. All right? That's the idea. Now, let's try one more problem where you have to fill the hole. The last type of problem you need to be able to do is fill the hole. This guy, normally I would say let's struggle through this factoring cubes, but in the interest of time, I'm going to tell you how this factors to speed it up. The denominator is difference of squares, which I hope you remember. The numerator is difference of cubes. I don't know if you remember that, but it's x minus 4 up front, x squared plus 4x plus 16. All right? Now, this graph has a hole in it. And if I were to graph this at 4, there would be a hole. I don't know. The shape is probably a big mess. It's probably kind of linear-ish in nature because it's x cubed over x squared. It kind of behaves linearly, but there's a lot going on. There's a hole at 4. The question is, write a piecewise function that makes f continuous at the removable discontinuity. In other words, I'm going to make a function that's almost identical to this one, but then I'm going to fill the hole so I have continuity. Now, at every other point except for 4, I don't have a problem. If, for example, when I put in 7, this guy would be 3 over 3, it would go away, and I'd have what's left. At 10, I'd have 6 over 6, they would divide out, and I'd have what's left. At -22, these guys would go away, and I'd have what's left. So at every point that's not 4, it behaves just like this because these divide away. So for every point except 4, it behaves just like x squared plus 4x plus 16 over x plus 4. Okay? Now the question is, what can I put here as a y value to set a point that fills the hole when x is 4? And this is where we use the definition of continuity. Remember, the limit has to equal the point. And so if I want to know what to make the point, then I need to know what the limit equals because they're supposed to be equal. So to fill the hole, take the limit as x goes to 4 of the function, which really you can just look at the what's left. What does the what's left approach as x goes to 4? And that could be used to fill the hole. When I put in 4, I would get 16 plus 16 plus 16 over 8. That's 48 over 8, and that's 6. The function wants to be 6. So if I put a point at 4, 6, I will have continuity. That answers the question. Determine the removable discontinuity. There's a removable discontinuity. I guess I didn't answer that question. At x equals 4. And then we had a piecewise function that makes it continuous at the removable. That's the second part of my answer. All right? All right. Try this one. Now, this one's gross because, man, it goes to solving and factoring cubes. Do you remember how to factor cubes? That's pretty gross. I'll give you a second to think about it. Start with the denominator. You know it's x minus 7x plus 7. So surely if this has a removable discontinuity, one of those two guys has to be a factor. You could figure out how x minus 7 factors out from this one of two ways. You could do long division. X minus 7 into x cubed minus 9x squared plus 11x plus 21. You learned that in Algebra 1. I don't know if you remember it, but you used to be able to do that. And you also could say, what about 7 into, and use synthetic, 1, negative 9, 11, and 21. Now that was only last year, so I don't know if you remember that or not, but let's give it a go, shall we? Remember the process is, this is the 0 of the divisor or the 0 of the factor, and these are the coefficients. You start by bringing down the first number and recording it there, then multiplying, recording that product in the next column, and adding. Multiply, record it in the next column, add. Multiply, record it in the next column, add. If you get a 0 at the end, then it went in evenly. This was good. So that tells me that when I divide out x minus 7, what's left is x squared minus 2x plus 3. Do you remember that? I didn't think so. Okay, so back to the question. It said, where's the removable discontinuity? You should be able to answer that. There's a removable discontinuity or a hole at x equal 7. In terms of filling the hole, making a piecewise that fills the hole, at every point besides 7, so at everything besides 7, x is not 7, it would just be the same as, behave exactly the same as this. Again, at all the other numbers besides 7, these just subtract, divide away, and you're left with the what's left, x squared minus 2x plus 3 over x plus 7. The question is, what about when x is 7? What single y value should you use to make a point that fills the hole? To do that, how do we do that? Well, over here, remember we did the limit. We take the limit on x going to 7 of the residual function and say what happens. Well, it goes to something like 49 minus 14 plus 3 over 14, right? So, let's say, oh, it's minus 3, sorry. I have an error there. You probably were shouting that the whole time. This is minus 3, yeah? Minus 3, minus 3, minus 3. So 49 minus 17 is 32 over 14. That's 16 over 7. And that doesn't reduce. So to fill the hole, we would use a y value of 16/7. We exit 7 and we fill the hole. All right. That's the last kind of problem. You should be all set to go on the homework. Hopefully it'll go well, and on Monday you'll practice it further. Have a great weekend.